Right. Welcome back from the break. We're very happy to have Rose here from UC San Diego, and she'll be telling us about automatic symmetry discovery from data. You go ahead.
Hi, everyone. Thanks to all the members for inviting me here. It's been a long time since I visited Boston. I was in Boston. I think summer was the first time in Boston. Thank you for doing this. I'm Rosie. I'm associate professor at UCSD. So I direct the spatiotemporal machine learning lab. We're in the CS department, and our goal is to advance machine learning for large-scale spatiotemporal data. So today I want to talk about some relatively new work from our group on automatic symmetry discovery from data. As you all know, okay. As you all know, symmetry is everywhere, from alloy leaves to the snowflakes to scientific problems. So there's also symmetry in the design of deep neural network architectures. In fact, symmetry has been used as an inductive bias to design neural networks for a long time. For example, in convolutional neural network, people use translation symmetry to design the filters that are shared across different coordinates. In image data for graph neural network, people exploit the permutation symmetry of the data to wire the weights in the neural network. And this field of injecting symmetry into the design of neural network architecture is known as equivariant neural network or equivariant deep learning. So equivariant deep learning has made a lot of success in AI for science, from particle physics to protein design to molecular dynamics. And there are a lot of usage of equivariant neural networks for all kinds of prediction problems. However, they all have one major assumption, which is they require known symmetry as a prior. So they need to know what kind of symmetry or what kind of symmetry groups or group representations are already in the data, and then use this prior knowledge to design the neural network. The downside of this is, first of all, for very complex real data, we may not know all the symmetries a priori, and second of all, we need to design a separate neural network every time we encounter a new type of symmetry. So that basically leads us to this super ambitious goal of symmetry discovery. And we view this as a step towards AI scientists, and that's like the new baby of my group. So AI scientists, to build AI scientists, we wanted to look at symmetries because it has some fundamental connections with conservation laws given by Newton's theorem. And she said for every symmetry, there is a corresponding conservation law. So if we can discover the symmetry, then we can hopefully find the new conservation laws in the system. And with this kind of AI scientist approach, we can identify unknown symmetries to generate novel hypotheses, and then to help us discover new physical laws. Okay, some quick background of symmetry. I think this is probably very familiar to the audience here. As we know, mathematically speaking, symmetry is a group with a set, right? So group is a set with G as a composition map to itself, and an identity is an element in the set. For every element G in a set, there is an inverse element G inverse that also belongs to the set. So a familiar group is the special orthogonal group SO2 and represent 2D rotation. So if I rotate this object clockwise 60 degrees, then the inverse element would just be to rotate the same element counterclockwise by 60 degrees. So symmetry manifests itself in two definitions. One is called invariance, the other one is called equivariance. So if we have a function f, and this function f can represent your predictor, when we rotate or when we transform the input x by this group action g, then if this group action actually doesn't change the output of the function, we say this function is invariant with respect to this group. More generally speaking, if we transform this input G by this group element, and this transformation automatically applies to the output of this function, then we say this function is equivariant. So it's obvious that if we set the right-hand side of this equation for equivariance to be identity, like the group element to be identity, then the equivariance definition reduces to the invariance definition. So then we can see invariance is just a special case of equivariance. So for the type of problems specifically for dynamical system learning, we can look at this very simple example of predicting fluid flow. Let's say we have this kind of fluid flow in the Eulerian grid, and then the function here represents a simple function of scaling the velocity field. So if I scale this velocity field by 2 and then rotate it 45 degrees, if it gives the same result as I rotate m scale, then this function is equivariant. So the transformation imposed by the group action and the function itself commutes, then this function is equivariant. So the idea of equivariant networks is to build networks that can approximate such function. And a typical way to do that is similar to the idea of convolutional neural network, which is through weight sharing. So look at this example, given the image here, where each square represents a pixel. So translation symmetry is encoded here in the neural network where we enforce the weights on the orange blocks are exactly the same. So when we shift the features from top left corner to the bottom right corner, the representations become exactly the same. In this case, convolutional neural network or CNNs has translation invariance. We can generalize this idea from the group of translation to any group. This is given by the theorem in Weiler and Theta 2019. So this paper gives a beautiful sufficient and necessary condition for constructing any equivariant convolutional layer. And it basically said if the convolutional kernel in my neural network satisfies this equality, then this convolutional layer is equivariant with respect to the corresponding group. So this equality basically says the representation of my group element when I left multiply and right multiply the kernel of the convolutional layer, it doesn't change the output of this convolutional kernel output, then this condition basically ensures that the convolutional layer is equivariant. This condition is also known as group invariance under conjugation. So the art of designing equivariant networks boils down to solving linear equations. And we can solve it efficiently through all kinds of tricks, and that basically give rise to a lot of different papers in equivariant deep learning. Okay, so, but I'm not going to talk to you about how to design these neural networks, right? We're trying to tackle a slightly different meta problem of discovering symmetries from data. And obviously, our group was not the first one to tackle this problem. So there has been some prior work to discover symmetry from data, one of them being the meta-learning idea in IAIFI 2021. So as I mentioned, designing equivariant networks requires us to share parameters within the neural network. So the idea of meta-learning symmetry is to use another neural network to learn how these parameters are shared in the neural network. Right, so they basically parameterize the network layers to represent different sharing patterns. And then they use meta-learning, which is learning to learn type of idea, to learn how these weights are wired together. And then the downside of this problem is that the complexity of this method grows linearly with the group size. So obviously it cannot handle the non-continuous group or really large groups. Okay, then there's another related work by Andrew's group in 2020 called Algorino. So this group actually has some cute idea where they take a Bayesian approach of automatic symmetry discovery, where they assume there is a distribution over all the possible group transformations. So I show in this animation here, if we have all the possible transformations available in the blue rectangle, then we will use algorithm to penalize the type of transformations that will leave my data invariant. So we will find this subset of transformations in the green box through the regularization approach. So it biases the model towards learning a solution that is that it can keep the data distribution invariant. But this method, even though the title is learning invariance from data, it actually assumes that we already know the group. They just wanted to learn the amount of transformations for a given group. So it's not actually discovering the unknown group from data. So now that comes to our prior work, led by Nima. I think he's given a talk also in this workshop later this week. So this idea is trying to redesign how we think about convolutional layers by approximating a group convolution with very small actions on the data manifold. So we introduced the idea of Lie algebra basis to approximate the group convolution. So this Lie algebra basis will move the data element little by little to the target destination on data manifold. This idea of LieConf can learn unknown groups from data, but at the cost of high computation. So what we desire is a kind of method that can learn symmetry from data efficiently and then can generalize to large groups with possibly infinite number of elements. So this is the work published last year at ICML, led by my PhD student, Jianke Yang. And it's called generative adversarial symmetry discovery. So the idea here is we're going to think about the problem of symmetry discovery as a generative modeling problem. So we have this data set, let's say we're looking at MNIST, right? The MNIST data set is the distribution of all possible pixels, and we want to figure out the invariance of this distribution that will keep the relationship invariant. So in this case, the relationship is the mapping from image pixels to the labels of this image. So when we transform this data distribution, hopefully this transformation will leave the distribution invariant in terms of joint distribution of x and y. So formally speaking, let's say we have a data set of input x, output is y, and then we have a distribution over this. So we wanted to learn an unknown function that can map from input x to output y. We want this function to be equivariant, which means that this group transformation with the representation rho here will commute with the function f. So we want to solve this problem under the condition of unknown group, unknown representation, and we want it to be efficient computationally and hopefully applicable to a broad class of symmetries. So we use the machinery of Lie group. As we know, Lie group is a continuous group with a smooth manifold like this green ball, and Lie algebra is a tangent space at the identity represented by this pink plane. So the beautiful thing about Lie algebra is it can be transformed into the tangent space at any group element. And with this tool, we can build a new type of generative model, and this is called LieGAN, right? So if you're familiar with the concept of GANs, it basically have two neural networks playing a game with each other, right? So we have a generator that tries to generate the data, and we have a discriminator that tries to discriminate between real and fake data. But the idea of LieGAN is actually different. So instead of generating data, we're trying to generate group transformations. But the concept of adversarial training applies similarly here. So we have a generator that will generate new group transformations. And then we have a discriminator that discriminates between two sets of distributions. So this set of distributions corresponding to the original data distribution, x and y. So I'm using like particle trajectories here for this audience. And the corresponding transformed data distribution is a fake distribution. So when the discriminator fails, it means that the model cannot distinguish between the original data set and the transformed data set. Then we have successfully discovered the invariance in the data. So if we go back to the generator again, right? Then here we can see that we use the tool of the algebra. So the L represents the algebra basis matrices, and then W represents the structural coefficients in the algebra. So both of these things are learned from data. And we impose a prior distribution over the structural coefficients such that the group is actually uniform along the group orbit. Okay. So to summarize, we have this new type of generative model that parameterizes distribution over continuous Lie group. So we want to learn the generator and the discriminator simultaneously, and then we can use a loss function that is similar to the GAN loss, which is to minimize the Jensen-Shannon divergence between two sets of distributions. And the difference here is that the generator now is learning the distribution over group transformations, and the discriminator is trying to discriminate between the original data distribution and then the transformed distribution. We can show that this generator actually is optimal in the sense that the generator can achieve zero Jensen-Shannon divergence under certain conditions. In this condition, which certifies that this transformation has to be volume preserving, which is the case for orthogonal rotation group. And then under other conditions, this learned model will actually achieve optimum in terms of the discriminator. The discriminator will give us optimum performance under this condition. So let's look at the simple example of subgroup of SO2. So for this data set, we generate a lot of samples using this corresponding function, and then the model only sees the data without knowledge of underlying group transformation. So obviously we know what is the Lie algebra basis for the special orthogonal group, right? Basically the three-dimensional data. And then we're just going to learn the corresponding group transformation, which is a 3x3 matrix. So we have this kind of data point clouds, and then we basically discovered the corresponding Lie algebra basis in this data set, and that matches exactly to the ground truth. And then this data will transform this side of the pizza pie to the other side of the pizza pie by rotating the data cloud. I guess what's more exciting about this work is that we did apply our method to the LHC data. And we got a lot of help from our physics friends in UCSD to understand the data. So if I said something wrong here, please correct me because I'm not an expert in LHC. My understanding is that we wanted to classify these jets when we accelerate them to very high speed. And during this process, we can discover the symmetries in the data. So our model, but just taking in these different momentums for different particles and trying to classify them into different jets, they can discover 7 different Lie algebra basis functions. And these 7 Lie algebra basis functions actually corresponding to the well-known Lorentz group from data. And I did a little bit of search about this. It turns out that Einstein trying to use Lorentz symmetry to derive his GR theory, right? What's surprising about this work is that the model doesn't have the type of knowledge as Einstein, but can still discover Lorentz symmetry from data. And to verify this method, we use the discover the symmetry to design a neural network, right? Similar to many of the equivariant network idea. So once we discover the symmetry, we can use the symmetry to constrain the weight sharing patterns in the equivariant neural network, and that becomes a new type of equivariant neural network. So this is trying to show the classification performance for this problem. And eGNN is an equivariant GNN, which doesn't have Lorentz symmetry. And then LorentzNet is a neural network that has hand-designed Lorentz symmetry in the architecture. And LieGAN is using the learned symmetry to design the neural network architecture. I guess what is quite interesting here is LieGAN, without any domain knowledge about LHC data, can actually match the performance of Lorentz net. And I know these Lorentz net were basically the result of many brilliant scientists coming together and figure out how to wire these weights in a neural network, right? But then here, we're using a model to discover the corresponding symmetry. Okay, and just to follow up on this work, the example I showed you on this like relatively lower dimensional data, but real world is actually quite complex, like these high dimensional reaction diffusion systems, or the data that evolves on the complex manifold. So if we just use the previous method to discover the linear transformations on the data, that will be an oversimplification of complex real world problems. So we feel that linear symmetry is not enough to describe the complexity of the data, so we try to generalize this work to nonlinear group actions. But we still want to use this idea of generative adversarial training, right, to figure out the intrinsic invariance in the data through two networks playing a game with each other. So that was the work actually recently presented at XML, and again led by my brilliant PhD student Tian Ke. So the idea is that, well, instead of discovering symmetry in the observational space, which can be quite complex, let's try to find a latent space that hopefully is much simpler and then apply our method to it, right? So that's a very straightforward idea, but it has to be done carefully with some caveats. So the idea is that, okay, we have this input data, let's say these this triangle represents data points scattered on some high dimensional place, and you can see that the transformation here is actually not quite uniform. It doesn't correspond to the linear action. So just to clarify, though, these triangles represent the samples along the LV trajectory. I think Patrick talked about the Lopta-Volterra system. So each of the points correspond to random samples along Lopta-Volterra system, and the symmetry here is nonlinear. But once we transform that into a latent space V, then the transformation now becomes linear. So it has a perfect circle, right? So we can formalize this problem by saying that this transformation actually can be decomposed. And the original transformation, pi prime, can be decomposed into three parts: a mapping from input to latent, and then the transformation happening in the latent, and then the transformation from the latent back to the observational space. So in this way, we still constrain the latent space to have linear transformation because it's much more interpretable. But generally, we can have nonlinear transformations in the observational space. So the careful thing we have to do is that we need to restrain these transformations to happen to a data manifold, right? So the mapping from data to latent has to be restricted to the data manifold, which means we need to assume that given high dimensional data, there is an intrinsic lower dimensional representation that we can map the data to. If this kind of data manifold hypothesis doesn't hold, then this method probably won't work well. But luckily, right, from the massive amount of literature in compressive sensing, we know a lot of high dimensional data have low dimensional representations. So in this case, if we have the manifold hypothesis, then if you look at this equation, right, you basically have the mapping of phi from data to latent, and then the inverse mapping from latent to data. So these two things actually are inverse of each other, and it forms an autoencoder. So if we lift the data action, the group action to the group manifold, then we have a perfect autoencoder that's operating on the observational space, and then we can still do the transformation linearly in the latent space. So that basically is the architecture of LieGAN. It's quite straightforward after I explained the rationale to you. So the idea is that we have these, again, generators that generate the group element, but now you can see we have the data that map into the latent space through an autoencoder. The encoder maps the data to latent space, the decoder decode from latent space to output. And then we use the discriminator to discriminate this data distribution before and after transformation, right? So this is the autoencoder architecture that tries to figure out the latent space. And I will show you later on that this latent space is actually quite useful and can be adapted for many different tasks. So to do this carefully, we noticed that sometimes if we just apply an autoencoder to the data, the latent space may not be well structured. So there are two constraints that we impose on the latent space. One is disentanglement. Right? So the idea of disentanglement is that we want the latent space to be interpretable, meaning they can be decomposed into interpretable elements. Let's say we have these airplanes that are, high-dimensional data images. So we can decompose them into interpretable latent representations by looking at angle and color or lighting. And then we can pose that by basically constraining the latent space to be the direct sum of smaller latent space. And the other regularization is trying to avoid some trivial solutions with bias. So in this case, if we have the original data in blue, and this data is actually centered in 1, so there's some bias in the data, but the model will learn to actually transform data in a different way. So we have to correct the origin in the data. So in this case, we basically just apply batch norm to the center at the origin to make sure the data is actually centered in the same point, and then the group action can act correspondingly. In terms of use case, right, one very exciting use case is that we can use these type of symmetries discovered by a model to reduce the search space of possible governing equations. So this is actually built on some wonderful work by Nathan and all, which you can automatically discover equations from data. But here, we wanted to show if you further add symmetry inductive bias, you can make the equations much more simpler and easier to interpret, which is really the idea of Occam's razor, right? So we have this complex reaction diffusion system, and the data looks like a video, so it's a relatively higher dimensional system. And then we can use our method to find the latent representation, which is here corresponding to the state space of the system in this circle. And then we can use the discovered latent space, right, to reconstruct the data. You can see that perfectly reconstruct the data. And then if we actually use linear symmetry, it will actually lead to noise. So that shows the critical importance of using nonlinear transformations in this case. So we can then apply the latent space to find the governing equation. But let's say we have the latent governing equation as z dot equals some functional operator f of z. So we can fix the encoder and just optimize for the parameters of this equation using this z as a new coordinate of the equation. So we can optimize using this loss function, which basically minimizes the trajectories in the latent space against the original data set, right? So we basically map data set to the latent space and then optimize for the parameter theta. And once it's done, we can find the corresponding theta for this governing equation. And because the coordinate v is symmetry regularized, so it is much more better behaved than a regular latent space formed by autoencoder. So we can see that if we do have symmetry, the latent space is perfectly well behaved. And then we can show that if we add the symmetry, right, into the Sandy method or Sandy autoencoder method, then our equation has perfectly symmetric parameters. And then we have only 2 terms per equation. But here, if we just use a vanilla autoencoder and apply Sandy to it, then you ended up with equations with a lot of redundant terms in the equation. So we can use this latent space further to do long-term forecasting. I think Patrick mentioned some work on neural ODE, right? So the idea here is once you find a really good coordinate or latent space V, then you can forward simulate using the discovered equations, and that gives us much more stable long-term forecasting result, as you can see in terms of per pendulum and LV system, right? So it basically shows for a high-dimensional system, if you find the right latent space, that can actually alleviate the error propagation issues mentioned by many audience here. To summarize, right, and I laid out this very grand vision to discover symmetry of data automatically without any domain knowledge, and that is an important step towards AI scientists. And what we hope is that we can, allow AI to comprehend massive amount of data using multimodal data, including numerical data I showed in this talk, and hopefully text data based on relatively newer development from foundation models, and maybe image data. Then this model can consume a huge amount of multimodal data and come up with new scientific hypotheses. And then in that case, our real scientists sitting here will just be able to enjoy the beautiful beaches in San Diego, right? While the machines are doing the work for you. So with that, I wanted to publicize that we are hiring postdocs and PhD students working on foundation models for science. So if you're excited about this line of work, please feel free to reach out to me by email and follow me on social media. So I want to thank the funding agencies for supporting this work, and happy to take any questions.
Thank you very much, Rose. Questions, if any?
Thank you for the talk. Correct me if I'm wrong or not. In both cases, your generator is just linear. It's just a linear number.
That's right.
It's not a deep number.
The generator G is just a linear matrix.
It's just a linear number. And can we use this setup for discovering gauge symmetries?
And that's exactly the problem we're working on right now with two interns. So we're looking at gauge symmetry. So the short answer is yes, but with some careful design of the coordinate system, right? Because there's a reference frame problem that we have to solve from gauge problem, and two, the type of real world data that actually has gauge symmetry. But we are working on that problem right now, and we do see some very promising.
Thank you.
Thank you for a very interesting talk. I have a very general question. How do you design your discriminator so that it doesn't bring any bias, like it's equally sensitive to different types of symmetry? Just imagine if you have a convolutional network as a discriminator, it naturally sensitive to symmetry groups that are having like rotational invariance, and it brings you a prior knowledge to your discovery.
Let me see whether I understand that question. So because your discriminator is a neural network that tries to discriminate any two distributions, right? That you want your network to be as powerful as possible. So if your data has some, let's say if your image data has translation symmetry, you wanted to use CNNs to do that. You just want to build the most powerful discriminator possible.
Yes, but I mean, different discriminator is sensitive to different symmetry.
Yes, but because if you wanted to, I mean, in general, I think by universal approximation theorem, if you have enough layers and depths, then you can do pretty well, regardless of the design, right? Because it's just a classification task.
Yeah, but still it's bringing a prior knowledge.
Then you will have some sample complexity issues. Let's say if you have inductive bias in translation, you see, and then you will have fewer samples. You will need fewer samples to learn, right? But it doesn't affect the symmetry discovery performance, right? So we want this discriminator to be powerful enough to be able to distinguish.
Right.
I'm not sure. Yeah, maybe I can discuss with you offline.
Yeah,
I'm not sure I entirely follow your question.
Yeah, thank you.
Hi, thanks for the talk. So you had a slide about Lie convolution. So you were basically constructing the group element by a sequence of Lie operations. So Lie group elements satisfy the first order differential equation. So I wonder if some of the stuff that Patrick was talking about, where can you think about it as a neural ODE, that the transformation that you're trying to actually accomplish, can that be implemented as a neural ODE, because it's effectively a neural network with infinite number of layers.
Yeah, exactly. That, I mean, that's actually something we responded in the rebuttal with some reviewers. So that's,
That was me.
yeah, so in some sense, there's some analogy with like outcomes versus neural lead. You can do like infinite number of lead operations to move data over to the other, right? But the design here is that in neural lead, you use a neural network to approximate the derivatives. But here we use a neural network to represent the group elements. So there is a finite completion here in our formulation of the LaLieGAN.
Thank you.
Yeah, thanks for the great talk. I had a more general theoretical question about just discovering this idea of discovering symmetries. I know there are instances where some manifolds admit more than one Lie group structure. So I was wondering, have you run across that when you're trying to discover these symmetries? And if you do have more than one structure, how do you choose between them, or does it actually matter for your applications?
Yeah, I mean, that's a great question. So in fact, in the follow-up work of LaLieGAN, like this paper I mentioned, so for LV system, right? Actually, for LV system, I kind of show here, we can have like more than one symmetry. So the way we regularize this method to have like relatively different symmetry discovered by the model is to regularize against the similarities of group elements as part of the loss function, right? So it learns to learn multiple symmetries that are relatively distinct from each other. And therefore, the model is able to find multiple symmetries from the data. But then in the case where, you know, the two symmetries have some sort of conflicts, it becomes a challenging case, right? Because it's not possible for the model to know like exactly which symmetry we're favoring versus the other. So we can do that through some additional explicit regularization. But I agree there's a lot more that we need to be worked out.
Oh, thanks for your great talk. But I have a question. It's like I feel like your method could be only used to deal with symmetry group that is homomorphism to translation group real line or torus instead of very general symmetry group. Is that correct?
I think we showed a lot of like very general groups, so it's not only limited to Fogg groups.
But it is homomorphism to translation on real line or torus. Is that?
I think we showed more than that in our experiment.
Okay, thanks.
Beautiful beach in San Diego, but there's also earthquakes. So is everybody okay after this morning? In Southern California?
No, I think the earthquake line runs past San Diego, so it actually, like LA is along the San Diego, like the earthquake breaking, not San Diego. That's like the lovely part of San Diego compared to
So
LA.
more of a comment than a question. So in the line of work that led to this, I would like to draw attention to the work by the Florida group, where we were working in a very similar context, where we were thinking of automatic symmetry discovery with no prior knowledge. We were working in a supervised context, so we did have an oracle, at the very least numerically given. We did a lot of these examples, including the example in these digits. And we also have a couple of examples of gauge theory. So we discovered the standard model gauge group and the SU5 grand unification group in a field theory context. And yeah, so I highly recommend for the audience to read our papers as well as a supplementary reading, because they were seriously, because they were written by particle theorists. And you're a computer scientist, so we bring complementary views on this subject. So
Absolutely, yeah. We actually read many Constantine's work with me and my students. So we're trying to. I think Jesse also did some wonderful work on symmetry again that we use as baseline in our paper. So indeed, I encourage everybody to look at these papers, and they're also mentioned in the third section in our paper. And I do agree there is a much broader community here beyond just computer science centers like me. They're trying to do this, and I'm glad that we are having workshops here to exchange ideas and also look for feedback. And if you have good examples of gauge symmetry, I'd love to learn about them. Sure. Try to apply that method to that.
Hi, I really like this stuff. So as you mentioned, most of the Lie groups that we actually run into in reality can be embedded into a general structure, right? A general linear structure. Could you just speculate how we would go about discovering such Lie groups that cannot be embedded into a general linear group?
I guess like one idea is that, well, let's not constrain the latent space to linear. Let's allow more structures in the latent space. But the upside is, the downside is that if you give too much flexibility in the latent space, then the model can become like too flexible in some sense. You basically ended up with a super non-interpretable latent structure. So I hope there is some sort of inductive bias that you know about how these Lie groups behave, whether there are some general properties that you know about these Lie groups, and then use them to constrain the latent space. Right? So I think operationally that will lead to a slightly different autoencoder that will learn the latent representation in a different manifold rather than linear subspace. I'm not sure whether that answers your question. Yeah. Okay.
Last question.
So I have a question about, very small question about, discovery of Lorentz symmetry from LCD. I think the LieGAN, you said that the LieGAN found 7 generators, but I agree that the Lorentz group only has 6 generators, so what we did is one additional generator.
Yeah, I don't know why it actually generated 7. There's actually a redundant generator here output by our model. I'm not sure why exactly. Maybe we didn't apply the regularizations like strongly, but then we did try that with stronger regularizations in the latent space, then actually compete some of the generators in the discovery. So exactly how we ended up with 7, I'm not sure. But I would appreciate some insights from LHD data.